Right, so here we go. We're already on the fourth lesson of the program, so that's good. We're talking about functions now. And really, we're just talking about big picture stuff. We're not going into all the details yet. That's something that's going to come later, where we really kind of break down some functions, different classes of functions, and so on. But for now, here's some general overview stuff. Okay, so functions in general, whenever we think about a function, think about instead of in math terms, think about what they are. And they're methods for us to model the real world, okay, and make predictions about things. And so if you think about functions that you see in college algebra or trig or even in calculus, they're not that applicable on their own, right? The idea of functions is an important idea, but them by themselves, they're these one-dimensional objects, right? So they don't by themselves don't mean a whole lot, but I want you to think about the big idea behind them all. Okay, it turns out that the principles that we use to deal with these one-dimensional functions in calculus can be applied to the three-dimensional world. So the rules stay the same. So that's why it's important to learn the rules in the simple cases here. Okay, so what is a function? There's a lot of ways you can look at it. I think the easiest way, at least to wrap your head around it, is it's an input output machine. Okay, in other words, you plug something in and you get something out. Okay, that's a function. And ideally, when you plug something in, whatever you get out, you won't get something different out every time you plug in the same thing, right? If you put a quarter into a machine and sometimes it gives you a Coke and sometimes gives you Dr. Pepper, right? Without you telling it to do either one, that's probably not a good function, right? You want it to do the same thing. If I push the Dr. Pepper button, I get a Dr. Pepper every time, right? That's a good function. And so there's a lot of different ways we can represent functions. For example, let's see, here are some functions that we can talk about, although these are completely in words. You know, the jetliner that is changing altitude as its distance from the starting point of a flight increases. So you think about, you have a graph here, right? And we'll say that the x-axis would be a distance, and the y-axis is another distance, but we're talking about, you know, vertical distance, so altitude. And so, you know, if the plane is taking off, as its distance from its starting point increases, well, you'll see that the height, the altitude will change as well, right? So that could be one function. We just represented something in words graphically. Also, you know how children will grow. I know that well at this point. They grow a little bit too fast sometimes, and you can't keep up with the right size clothing, right? But let's say they are at, I don't know, 1 month, 2 months, 3 months, so on. And then, so that'd be their age in months. And this can be their, let's say their height, or no, we're talking about weight. Let's say their weight. And so, of course, you know, they're born at a certain weight, and then they grow, and, you know, they grow pretty fast the first few months, right? And so you might see something like that until they level off. Okay, so anyway, these are representations of functions, okay? Although we typically don't think of these as functions. So some good definitions to know would be domain and range. Okay, so when you think about a domain, you should be thinking about what the x-axis or the independent variable is doing. That's typically your domain. Now, it doesn't have to be x, it could be any letter really, but that's going to be the inputs. So domain, think inputs. Okay, and then the y-axis, which typically the y-axis, again, doesn't have to be y, it can be anything, any letter. And that would be the range. Think outputs. Okay, so really when you hear domain, think what are you plugging in? Range, think what's coming out. Okay, these are also called the independent and dependent variables, right? All right. And so, let's see, yep, done with that slide. Let's talk about the definition of a function. So here we have a relation. So we have 3 points, okay? 3 ordered pairs, I should say. And typically when you see this, this is not specified in the problem, but typically when you see this, you know that this is an x value and a y value, an x value and a y value, and so on, right? That's why they call it an ordered pair, literally a pair of numbers in order, x and then y. Okay, and so let's kind of dissect this as a potential function here. And we'll talk about the definition in a second. Let's say we have our domain. Remember, that's our inputs. We have our range, or our outputs. And our domain would be 3, 2, and 3. Okay, 3 happens twice, so I don't need to put it twice. Okay, and my range would be 1, 4, and 2. 1, 4, and 2. Okay, and so, you know, sometimes you see it drawn out like this, your domain and your range. And let's see what the correspondence is, okay? How are they connected? Well, these points up here, right, these ordered pairs connect. 3 is connected to 1. Okay, 2 is connected to 4. 3 is also connected to 2. Now, remember what I said earlier, right? A good function is one where when you plug in 2, right, you plug in a number, you will always get 4. You always get the same value no matter what. But look what happened with 3. If I plug in 3, there's 2 potential options here. I could get a 1. I could get a 2, right? And so this is not a good function. And actually, it's not a function at all. It fails the function definition. So this is not a function. It does not meet that definition. Okay, and so let's kind of formalize that a little bit. A function, let's see. Okay, so this would be a function if every element in the domain, right, if every x value matched up with a single y value, okay? Every x value must match up with a single y value. Okay, now it's possible that 2 different x values share the same y value. Okay, I think we have an example like that in a second, but that's okay. You just don't want an x value giving you multiple y values. So not a function. All right, let's see if this one's a function. Maybe we get a function this time. Okay, here's my domain. A, C, and D, right? A, C, and D. My range, B, B, and C. So 2 B's, so I'll just write it once, and C. Let's see how it pairs up. A will automatically connect with B. C connects with B. D connects with C. Okay, so now I see that I have 2 x values that are sharing the same y value, right? But that's actually okay, right? All I want to avoid is an x value that shares 2 different y values, right? I don't want that. I don't have that here. Every x value has only 1 arrow leaving from it. So this one's good. This one behaves well. This is a function. Again, if you were counting the x values here, A, C, D, I have no repeats. Okay, probably a function we're dealing with here. Okay, so now let's talk about a little bit of notation. Okay, and it's surprising how often people mix up this notation, this f of x part. Okay, it's surprising because people will continue to read that as multiplication when it is clearly not multiplication. Okay, it is just notation to let you know that you are dealing with a function and what the input or the domain is supposed to be. What are you looking at as the input? Okay, so the notation y equals f of x just means y is a function of x. It's telling you that x is the input and y is the output. Okay, and you really want to keep those ideas together. X is the input, y is the output based on this notation. The letter x represents the input value, independent variable, y is the output. Okay, so that's exactly what I just said. Okay, and so let's use function notation to do this problem here. And this one's kind of tricky, but this is a good way to talk about piecewise functions. So this is one we drew out a second ago, but I want to use function notation here. So f of x, right? And remember, f of x is basically what follows that is a formula that will give you y values, right? So the function, I'm going to use this brace right here so I can break it up into pieces. This is a piecewise function. Is b if x equals a, or if x equals b. Okay, so either one of those happen, then you get the y value b. Okay, so this is just a rule. And then the y value is c if x equals d. And so from this formula right here, from this formula, this function, you can actually get all of these ordered pairs, right? If you said, well, what's f of a? Well, then you would look at this and say, well, when x, right, that was an x, when x is a, y is b. What about, what is f of c? Oh, wait, I messed that up. That should be a c, right? We don't have x being b anywhere. It's a and c, so that should be a c. Okay, f of c. Well, when x is c, y is b. Okay, and so this is where we get those ordered pairs. Okay. All right, this is a little bit easier to see because it looks like something we're more familiar with. Determine whether or not the relation represents y as a function of x. Okay, that's a way to ask if you plug in numbers for x, right? If you plug in numbers for x, is it possible that you get a single y? Okay, you get one y every time, not multiple y's, just one. And so one way you can do that is actually just solve for y, get y by itself. So, right, I guess I'll work this out by hand, showing these steps here. Subtract 5x from both sides. I'm rearranging it to get y by itself. So that way I can understand this function a little bit better, or this potential function a little bit better. Divide both sides by 2. Okay, and so if you can get it to y equals some statement here, and there's no other y's, then this is a function, right? Because you can imagine, we're not going to, if you plug in a number for x, let's say you plugged in 0, you would get y equals 5. If you plugged in, I don't know, 2 for x, you would get y equals 0. So every x value you plug in will give you a single y value out. And so therefore, we would say that this one is a function. Okay, what about this one? Y is a function of x. Well, x equals y squared. Let's get y by itself. In order to do that, I would do the square root of both sides, right? I use the square root property here. And what that's going to give me is y equals the square root of x, and y equals negative the square root of x. Okay, this is the square root property. We're going to talk about that some more another day. But anytime you have something like this, you just do the square root of both sides. Okay, now notice if you plug in something for x, you get two different y values, right? Let's say you want to plug in 1 for x. Well, you would get y equals the square root of 1. You would get y equals the negative square root of 1, which is negative 1. So not a function. You should only get one possible y value for every x you plug in. Okay, now let's work on evaluating a function. Remember, we talked about yesterday evaluating and solving. Okay, solving is whenever you are solving an equation like 2x minus 5 equals 11, right? That's an equation. You can solve it. You can find the missing value. Here, we're not solving, we're evaluating. We're figuring out what does this thing equal when x is -3. Okay, and so, all right, that's not hard to do. You just plug in -3 for x, right? 2 times -3 is -6. That's -11. Okay, notice this was not multiplication, right? That means f of x, what we did was we changed x to a -3. So in our formula, we should change x to a -3, right? That's what this means. All right, this one's a little bit trickier at least. So here we have where we're replacing x with -a. So don't even think about that too much. Just replace the x with a -a and then simplify. So 2 times -a is -2a minus 5. That's it. Okay, that's all you have to do there. So it doesn't have to be a number. It can be another variable. It can be several variables. Okay, oh, here's a fun one. So negative f of a. So that means negative that formula. Formula is 2x minus 5. Change x to a. Okay, and then we'll simplify that. Distribute the negative. So this is understood -1. That'll be a -2a. -1 times -5 is a +5. And there we go. All right, this is what I want to get to because this is going to be important when you take calculus, right? It's a plus h. Okay, you'll see that notation or something very similar to it. All right, so, all right, same as before. I'm gonna actually write it over here. I want a little bit more room to write it. Change x to a plus h. Oh, not to get carried away there. Okay, and then we'll simplify it, distribute the 2 to a plus 2h minus 5. And there we go. This, by the way, could be the solution that you're looking for. Not solution, but the result. It just depends on how far they want you to expand it out. So it just depends. Either one would actually be acceptable. All right, so here's a graph. I want to consider this graph, and I want to use the graph to answer these two questions, okay? So these are two questions, right? Evaluate f of 0. Let's do that one first. I'm going to do it in 2 different colors. So number 1 for evaluate f of 0. So in other words, when x is 0, what is the function value? Okay, well, this is my x-axis and my y-axis. So when x is 0, that's here, right? This is 1. This would be -1 and so on. So 0 is here. That point is 0, 1. So f of 0 is 1, the y value. Okay, second question says solve for f of x equals -3. All right, so what does this say? Remember, function values are the y values, right? F of x equals y, right? We saw that in reverse earlier. Function values, functions give you y values. So if the function is giving me a y value of -3, well, where's that happening at? -3 is 1, try that again. 1, 2, -3 is here. And so where is the function at when y is -3? Two places, right? This one is -2 to the left and then down 3. This is 2 to the right, down -3. Okay, and so the question, solve what is the function, or solve for the x value that makes the function -3. We have two of them, -2 and +2. Okay, so hopefully you can see those two problems as being similar. Okay,